Okay. Now everything works. So everybody hears me in your answer?
Yes.
Yes. Almost everybody sees me in okay. Right. So today we work with this same application from last time, the image recognition app. And I'm going to strip away the parts of the code that we don't need anymore, and I'm also going to entitle this strange. I'm not going to have any kind of memory or properties of some object. I will keep these canvas size, threshold, interval. I don't need to classify anything or nearest neighbor. There's no learning involved today. I do keep the camera. I want to still initialize the camera. And then the process video frame. So this one, I think we probably don't need to classify things or draw some pixel matrix or threshold the matrix. So these things are not going to be useful. No more object properties like bounding box or counting black pixels. So I just keep everything I need to display the video from the canvas. Delete, delete. No more drawing of the pixel matrix either. And then these vector operations, they can be here for usefulness. I think they will be useful. I'm going to rename also the title in the document here. And no need for these input or learn button or whatever. I just want to display two canvases and initialize them with whatever comes from the camera. So this is what happens here. I save the file, refresh the page, and that's it, more or less. So I'm just using the video input here, and this one is a blank for now. Okay, so what I want to do now is detect green color, right? So it's going to be some green object in the screen, hopefully the only green object in the screen, but the background is constantly changing, so let's see how that one is going to work. So how do we end up detecting green? This kind of green marker thing on the screen. Well, one step to start is let's tell it what color to look for. So green is going to be 0 red, 255 green, and 0 blue. So this is RGB, an RGB vector, okay? So 3-dimensional vector depicting a color. So maximum green and no blue or no red there. And I will use that global variable soon. But now what I want to check here is our getGrayMatrix function. So what this was doing, it was processing this one-dimensional array of numbers coming from the video itself. I'm going to reuse this function, and I'm going to call it something like identify pointer. Let's call this our pointer now. So our function now is going to identify where this pointer is going to be in the image. And we modify this function. We won't need the matrix anymore. I don't want to do matrix processing, matrix calculations, but I still want to obtain pixel coordinates here. So note that matrix of I and j, so at I and j, these are coordinates in the xy scale, right? So I and j of the matrix is going to be the column row in our canvas, more or less. So they will be useful, but I won't need the matrix itself. Now, our pointer, let's identify it by all the locations that are green. So anything that is green on the screen, I want to highlight. Maybe make it blue or some other color just for debugging purposes to see if we can identify the green color correctly or not. So, going through all the pixel values, here I have the RGB values. I could say, for example, if, okay, let's call it vector equal to RGB. So I made a vector containing the red, green, and blue values, so it's very similar to our global variable, the color value that we defined previously. So now if vector of 0 is equal to color of 0 and vector of 1 is equal to color of 1 and vector of 2 is equal to color of 2, then this is more or less saying that I have at this pixel at J and I, okay, at location J and I have exactly the same color as was defined on the top, so green. Fair enough. So let's say here a variable locations an array, and in these locations I'm going to push a new vector with J and I coordinates. So I just tell these locations that, hey, you will find the green color at J and I. So I find all the locations that are green. These things are not needed anymore, and I'm not going to return the matrix, I'm going to return this locations array. So identify pointer, it's going to give me locations where the pointer appears. So this is not going to be just one pixel, it's going to be more of them because this is a big green thing. And I want to get all of them. Now let's see if it works. So I'm going to say here console log locations. Okay, so it's easier to digest. I'm going to say locations dot length. So I'm going to print out just how many locations we have in the debugging console. I save the file. I open the console. It's F12 on PC, Google Chrome, and refresh the page. And I'm getting zeros, which is just fine because I don't show any green things yet. I'm still getting zeros because whatever green things I'm showing here are not pure green. They have a variety of different colors. Okay, so even now you can see here shadows and dark spots, and it appears that pure green is almost never to be found. Okay, so now the question is, how do I tell it I don't want a pure green color, but I want a variation of the green? So if we take a look at what this RGB color space looks like. So this is a 3D space where we can define 3D vectors pointing to some color in this RGB space. In this 3D space, we can calculate the distance between colors. We can say that two colors are more close to each other. It probably means that they look similar to each other. They probably have smaller distance between them. Okay? It may mean that they look similar to each other. So I'm going to calculate a distance between our initial color, global variable, and whatever colors the pixels are. And if this distance is small enough, I'm going to use a threshold. if the distance in this space is small enough, it means that it's some kind of green. It may mean that it's some kind of green. So let's try to replace the code with that and see what happens. I already have a function for the distance, but it was written in a very bad way. It only works for vectors with 2 dimensions. And now we have 3-dimensional vectors, right? Vectors can have many, many, many dimensions. Okay. So let's keep here like this and write that we're going to write a general distance function over here. And to make it general, you have to loop through all the dimensions. So I'm going to have a distance variable with 0. I'm going to loop through how many there are, 2, 3, 20, whatever, and just say that distance plus equals so first it's going to handle the first dimension because I is equal to 0, more or less the same as this thing here. And then I becomes 2, and then it's going to handle the second dimension, and then it becomes 3 and whatever. I could have made this one another plus here and then 2 there. It's the same thing, but this for loop is going to be a very powerful function later on if I need it in higher dimensional space. And when I return, I still need the square root of this distance, right? So these 2 variants are equivalent if they have just 2 dimensions, but now our function works for any number of dimensions. Great. Now, I'm going to go here, and instead of doing this equality check, which probably sounded to you like a bad idea anyway, I'm going to say if distance between color and our current vector is less than a threshold, do the same thing. So instead of equality check, we have a tolerance for nearby colors in the vector, in the color space. I save the file, and I try again to see what happens. Okay, 0. Not very helpful so far. So what is happening? Our threshold value is 100. So this could be raised, let's say 150. It's going to be a big value. Remember that 255 is the maximum thing, so let's try again. Ah, wow, okay, great. Something is happening. I'm not exactly sure what's happening because I'm not displaying the things that are green, but it sees some kind of close to green pixels, and quite many of them, like 500 when I do this. So it is detecting some green pixels, but I'm going to highlight them. Okay, I'm going to highlight them by drawing something on top of them. So let's see how we can draw pixels on the canvas. I'm going to say draw pixels at the locations on the canvas. Okay, let's put the canvas A first, and then say blue, so make them blue. This function doesn't exist yet, so it gets canvas locations and the color that I want them to be. And what I'm going to do is, I believe, first get the context, and then what? Yeah, I'm going to loop through all the locations. So the locations will tell me where to put the blue on top of the supposedly green, right? It's going to be the vector, the location. is going to be locations of I. And I'm going to make a very small rectangle, 1 pixel size rectangle, filled with this color that I give here as a parameter. So I'm going to say fill style is equal to color, so our parameter from the top. And then I'm going to say fill rect, so fill a rectangle at the locations, location of 0, location of 1, and how much width and how much height, it's going to be 1 pixel and 1 pixel. So 1 and 1 is going to be there. Yes, mistake. I think that this should be almost enough. I think now it should work. Hope for the best. Refresh the page, and now let's see what happens. Okay. Something is happening, right? I see some kind of identifiable blue thing there. It's not really what I expect it to be. I would like it to be all green. I mean, all blue. All the green turning into a blue. So this is something that I'm going to teach you how to do next. But, okay, first of all, I should tell the computer that, hey, you are looking for not the purest green possible, but for this specific shade of green. And I would also like my app to be very customizable. For example, maybe I get a green shirt someday, and then I want it to work with red or something else. I want to make it so that when I click on a color in this screen, it's going to use that as the base color. So then you can use any color marker you want and tailor your clothes or whatever accordingly. So let's see how we can do that. We already have here some kind of code that on mouse down takes from canvas A the cursor position, and let's say, how am I going to get now the color? I don't know, I don't remember, but I'm going to figure it out. So get color at location canvas HTML. I don't know. Okay. Get pixel color from canvas and mouse over. Okay, interesting. So I'm not going to zoom in that because I'm going to paste it here. But what I saw is more or less that I'm going to write this code here directly, even though we could have a function get color at location, right? But I'm going to say the canvas here is going to be in e.target, going to get the context from the canvas, and then I'm going to say to the context, get the image data at location of 0 and location of 1. And note here that again, I'm telling it to get the image data for just 1 pixel. This would give me, if I want a full rectangle of many, many different colors. But now I'm going to get it just for 1 pixel, and I want to put it in our color global variable. So the reason I didn't make a standalone function for this is more or less because it had the extra line of code here, so I didn't plan to put too much code. Okay, hopefully this works. So I'm gonna save it, refresh the page, and now if I click on my shirt, for example, okay, get cursor position. Yeah. Okay, I'm going to have to debug something is not working properly. I'm opening the console here and I will type color. Okay, our color is yeah, it actually should work, but I'm not sure what is this unsigned integer something. I'm going to assume it's doing some it's using some kind of objects there, and I'm going to say here specifically is equal to color of 0 is equal to data of 0. I hope it works. And then the same for the green and the same for the blue. So I'm populating them one by one. I think that somehow the color is changing its data type. Okay, yeah. So all the red stuff is now like that, and if I click here, it's not really doing exactly what I want, but it's doing something. First of all, the threshold is really, really huge. So we can play a little bit with that. Let's make it back. Let's make it 70, our threshold, and try again. So now I click my shirt. Okay, part of my beard, my hair, whatever. My shirt is a very, very dark red here. And in this room, I look like it's black almost. So if I really want to separate it, I would need to play with the threshold even more. Okay, and this green is also quite dark. So if I lower the threshold even more, wow, okay, well, almost good. I'm gonna click my shirt again. Okay, the white stuff on the background, the wall behind me. This should be very, very familiar to you if you know Photoshop or some kind of image editing software. There is this tool called the Magic Wand. So that tool allows you to select everything of a certain color, but it uses a tolerance. So it doesn't necessarily look at the raw color, it looks also at immediate colors. So a similar feature is there. But this one seems to be almost good. The problem is really something much more technical. The problem is the color space we are using. So now I'm going to teach you something very technical. I'm not going to go too much into details, but the RGB color space. The RGB color space does not have this type of relationship that colors that are near in the color space are also similar to human perception. So we are looking at the image. We are expecting all the green things to be grouped together, but they are not. In this space, even though here I move on this axis very much, the shade of blue just gets darker. To humans, this would just be quite a similar value, but then again, this moved almost halfway down on this axis. Also important to note is that everything on this axis is gray. So if you have equal amounts of red, green, and blue, you will have gray. And then from this gray axis, if you go equally in any direction, you will get all sorts of colors. So just keep in mind that the RGB color space is not meant for representing distances equivalent to human perception. There are others that do that better, but having said that, we could apparently use this more or less under good lighting conditions. to identify this marker. So now I have a very good, well identified location there with my with the threshold of 40. And our initial color, I had to click on this. So our color value is actually not a raw green. You can see how far it is from it. You look at it and you think it's green, but this is not nearly 255, and these values are not zero. They are very, very close to each other, in fact. But when you look at this picture, okay, you identify this as green because you are expecting to see a green thing. So it's more or less your mind playing tricks, more or less. Okay, but let's do one more thing and then have a little break. I want to teach you what the LAB color space is. And I'm going to teach you very rapidly and not in too much detail. But if you do attend color courses here in the department, then you will learn much more about these different things. So LAB color space is a color space that is more or less equivalent to the RGB, so that you can transfer from one space to the other all the time. This is a free color space. You don't have to pay to use this in your code. Some may have this kind of constraint. And the formulas for how to implement this are here on Wikipedia. And they are not extremely complicated. Okay, sorry, this is the Finnish page. Maybe I open the English because many people are English speakers. So what happens, the L component is going to be luminosity. So you can see what happens here when L is equal to 50, this is what the space is going to be, and A and B is going to be some deviation from one color into another and from one color into another. To be specific, A is from green to red and B is from blue to yellow. So having this L separately, we will be able to darken or lighten the values with just one dimension. And this makes good relationship between distance functions in the distance function in this space and human perception. You can read about this more or take courses about it, but let's just see what happens. I'm going to replace, to add one more function, and I'm not going to explain it. I'm going to copy it from here. I'm cheating. But the function is called RGB to LAB. So it should be intuitive what happens. It gets an RGB vector, what we were working on now, and returns some very complicated stuff. But I took these values, these formulas from Wikipedia. So if you go down here a little bit, you are going to see that there are some strange values here, like this 116, 500, 200, and much math and much proving involved. But I just took the final results more or less. So, and I implemented this. It's possible to convert. And now what I'm going to do is I'm going to go back to where I have the distance function. And instead of putting the raw color, so this worked. It worked in this room with threshold of 40. But I want to have it a little better. So let's see what would happen if instead of just putting the color values here, I first transform them into the LAB color space. And now my threshold is probably going to be different because the LAB values, they don't range in the same scale as here. They don't go from 0 to 255. LAB color values go from something I think they may even have negative values. Just a second. Okay, L ranges from 0 to 100, and possible ranges for A and B. Okay, they depend. Not very clear values here. But more or less it means that again we have to experiment with the threshold. I don't know how to find the values for A and B, but they could be something like minus some value, plus some value, or whatever. But let's try a threshold. Let's keep the threshold at 40 and see what happens. So I just added this new color space conversion, and we are now investigating what happens with the new system. Okay, so by default the green part is recognized, but this indicates that there is too much, the threshold is too big. So I'm going to say here threshold is equal to, let's say, 30. Okay, it seems to be isolated again, but now the situation is that it's more stable. You can see that I'm not getting those different shades of green anymore on the cap. So before, when we didn't do that, if I would rotate this or move it closer or further away, it would still show some green parts in it. So this is more or less the difference between changing first to a color space that resembles, distances in this color space resemble human perception. So it groups together light and dark greens better than if you just use the RGB color space. Okay, so let's have a few minute break, 10-minute break, and then continue with other stuff. So the threshold that we experimented with here and seems to do magic is 30. Okay, it would be way too much for my shirt, but this is another experiment. My shirt anyway looks really, really dark here. So anyway, our task is to identify this green stuff, and this green stuff works very well with 30. So we're going to set the threshold to 30. And now I'm going to talk a little bit. So we have here a function that calculates locations that are green, and we are calling the identify pointer to get these locations. But I would really like just one point, and the one like in the middle of the green area, more or less. And I'm going to get that by averaging the locations into one location. So pointer location is equal to average locations. Now I do have a function for average. It's here, but it doesn't really do what I want it to do. It averages 2 vectors, but now I'm going to have many vectors. I mean, many locations, many things that I want to average. So I'm going to just rewrite this function. And the locations come as parameter. Our result is going to be a new location. I'm just going to call it that and initialize it with 0, 0. And whatever it becomes, I will return it at the end. And I iterate through the locations, and I add to the first component of our loc variable the ith location and the first component of the ith location, and I'm going to do the same for the second. And now I'm basically summing up all the locations, all the components of all the locations. But this is not enough. I need to average, so I have to divide this by how many locations I summed up. So that's how you calculate the average. And now this should work. I should have the pointer location. And what I'm going to do now is draw a regular polygon. I'm going to use the second canvas, canvas B, the empty one till now. And wow, draw regular polygon, I even forget what it does. So location is going to be our pointer location. Radius, let's just put 4. Sides, way too complicated, I could just draw a circle, but okay, sides, let's put 8, and rotation, I don't even bother with that. It was already, it had a default value there, so I don't need to worry about it. So, I refresh the page, and so something happens. More or less in the right canvas, it's a trail, it's a trace of where I'm moving the marker on the left canvas. So I do get the average location. I don't print it here. I don't print it here because I want this to be just a test that I am sure it marks the correct pixels. But on the right side, I more or less see where I'm drawing with this. So this can be quite useful in your third project for next week. More or less the code that we have at the moment with a little bit of modifications, you can figure out how you can make, instead of these dots appearing there, lines or other things. I will talk a bit about projects at the end of today, right? But keep in mind that this is quite useful. And of course, if I'm going to cover this, then it's not going to work. So you can identify some similarities here between the events you can record with the mouse. Yes?
Your phone.
My phone.
Yeah.
Yeah, just a second. Thanks. I think it's useful that somebody tells me this. I'm not extremely disappointed because this is happening, because I plan to make this
I
lesson.
think you can
Yeah.
put this there.
Okay, underneath.
Yeah.
Yeah, so this lesson I wanted at some point to make a better YouTube video out of it, kind of like the one on machine learning. So I'm not totally disappointed if this video goes bad. But it may take a month or so. Anyway, yeah, so similarities between what happens on the right there and mouse events. So by mouse event, I mean these things. We were looking before at mouse down, mouse up, and mouse move. And this here can be seen the same way. It's more or less mouse down, mouse move, and mouse up is when I hide the thing, but now there is something green popping up, I think, somewhere in the left picture. Okay, this threshold may be 25. Okay. Where is it? Is it? I don't see it, but it's probably just 1 pixel or no, wait, I didn't save the threshold of 25, sorry. So probably a couple of greenish looking pixels appear from noise or whatever. This image processing is difficult. Okay, so now mouse up. Mouse is not down anymore, but mouse down and then continue to mouse move. So I'm going to teach you a little bit about events. okay? Because here it's quite nice. I just say listen for mouse down. And if you know how to write good code, especially in these event-driven languages like JavaScript, then you can have a code that is very easy to read by other people. I'm going to teach you how to make this mouse down, mouse move, or mouse up for our marker. Okay? So in the place here where I say I have my pointer location, I'm not gonna do anything with it. I'm gonna draw the pixels for debugging purposes, but what I'm gonna do is var event is equal to new event, and I'm gonna say here move pointer. I'm going to add to this event location is equal to pointer location, and I'm going to write we are on canvas A, dispatch event, our newly created event. So now I'm going to take out this draw regular polygon from here, and up here where we're listening for mouse movement, okay, this mouse down again is to record the color of whatever we want to track in our image. But I'm going to add a new event listener that is going to be pointer move. Move pointer, sorry. The one that I just defined before. So I made a code before that dispatches this move pointer event, and here I'm listening to it. And I'm going to say draw a regular polygon at the event's location instead. And yeah, I'm going to put it on canvas B still. So I save this function, I refresh the page, and the code still works, but the difference is now that I just have to write this. The part of the code that creates this move pointer event, it can be moved in a separate function, in a separate library, somewhere else, and the same way that the mouse move or mouse down or whatever, they are also embedded in the language itself. So now your code can be quite simple. It's just like looking for moving pointers, and when it's moving, then do something with it. And now I'm drawing with it. So the code can stay quite easily readable here. Okay. Yeah. Okay, a couple of more things we do today. What I want to do, I remind you that I want to draw some kind of circles. So these are just some dots there that I'm now debugging more or less, but I want to have a line to visually understand, is it a circle or not? And I'm going to calculate here, I'm going to store these equations in a variable called polyline. So this polyline variable is going to be a global variable, and it's an array. So it's going to be an array of points in order added by this move pointer function. And every time I'm going to, yeah, maybe let's not do that. Yeah, and let's go to the set interval function instead. Because here when we process the video frame, so we dispatch that event, but this happens every second. The reason why I don't want to do, okay, yeah. I will make a function here. When the pointer moves, it adds the location to the polyline and then draws the polyline. So I'm going to make a function that just draws a line from all the collected points that we have so far and see what happens. Draw polyline on a canvas and points. So this is more or less collected points every time I'm moving my cursor. And I'm going to use canvas B for that. Okay, and to do it, I'm actually going to go down where I have my draw line function, and I'm going to copy parts from that. But here is polyline, so it's a line made of many, many points, how many there are there. And we are going to move to the first point and its first component, so x more or less, and the y of the first point. And then we are going to just draw line to all the other points in this array. So for more or less like that. And I think that should work. So the difference now should be that my points there become aligned, become connected. This is not very optimized because I'm not clearing the canvas every time I'm adding new points. So if you would look closely, but it's hard to see, I think, on the projector. If you look closely, the initial lines become thicker and thicker as time passes by, because it just puts the pixels on top of each other. Okay, so to do that, to solve that problem, you should also clear canvas before drawing the new line entirely. Okay. So I'm able to draw something there. Okay, and now that line doesn't get thicker, at least I don't see it there. But our polyline object here, so all these 161 points, 210 points, or how many points are being added, this is more or less every time I make a new move of this cursor, it's going to add more points to this polyline and connect everything. Now, in this effect that I'm going to want to create, this keeping all of this polyline in memory is not going to be useful. I'm going to remove the first points of the polyline if they become too old. I'm only going to keep the last 2 seconds of this polyline into memory. I'm just going to remove the ones that are older than 2 seconds. So it's going to look kind of like a tail. When I move this, this marker like that, the initial part of the polyline is going to start to disappear as time goes by. So let's see how that one looks, and maybe we will understand better. Update polyline. let's call it based on time. Update polyline based on time. So otherwise it's unclear what I'm updating there. And polyline comes into memory. Now if I'm going to update based on time, I would like to have the time. So I'm pushing here the E location, the location of this pointer, but this location doesn't contain the time component. It's just the X and Y coordinates. It would be a good idea to have also a timestamp for each X and Y component. So to do that, I could, for example, do this, because JavaScript is just allowing you to do almost anything. So I could add to the location a time component. I'm going to comment this for a while just to see if it's there. So I refresh the page, I do something like this, and I print the polyline. So now each element in the polyline has a 0, a 1, and a timestamp. Okay, so this timestamp is the moment when this particular point, maybe it's this, was recorded. And in my function that says update polyline based on time, I'm going to say new polyline. It's going to be an empty polyline there. I'm going to iterate through this polyline, that is parameter. And if the time component of this polyline that was recorded the difference between whatever is now and that time component is greater than, let's say, 2000, so 2000 milliseconds means 2 seconds. If it's less or equal than 2 seconds, then I am going to add it into the new polyline. If it's older than that, then the new polyline is just not going to contain that one more point. So I'm going to add it there if it's not too old. And then I return new polyline. I save the file, refresh the page. So only the points that are in the last, recorded in the last 2 seconds. Yeah, there is this kind of effect here of lag from the cameras, and I'm really hoping that in Joensuu it's better, but yeah. So now I mentioned some time ago, and this is a bit chaos, this lecture today, for many reasons, but I mentioned that I want to make this as a game. So if you are able to do a proper circle, I want it to detect that you are doing a proper circle or near to a circle, and only then make that kind of effect, this kind of portal opening effect with some particle physics or whatever. So now we can see that I can even play a little bit with this speed. So I don't just have to do a proper circle, but I also have to do, because this polygon, whatever I'm drawing now, also closes in this time, but it's not necessarily a proper circle. What I want to do is make a circle, but also somehow guess this 2 second speed for making the circle. Because now I'm trying to make a pretty good circle, but I'm too slow. So the player will somehow have to try and figure out that, okay, my circles are too slope, and then when he gets the right speed, it's also the question, okay, is this a circle or is this not a circle? So two questions arise here. Do I match the correct speed, or is my polygon that I am drawing a circle or not? And this is what we are going to study tomorrow, a little bit more about this, these properties, but you can somehow see already that it's getting there. Like I am able to draw something there, and okay, we actually have a little bit more time. Sorry, I'm really confused today. So we can do a bit more. And we can talk a little bit about polygons in general. Yeah, so if you want to calculate the area of a polygon, now this is a little bit hard to understand the link, like why am I talking about the area of a polygon now, but bear with me. You can calculate the area of an irregular polygon if you know the coordinates of the points. There is a formula for that. For example, here you see this P1 point and his x1, y1 components. They also appear there. It's just this formula. So you take the first point, x1, multiplied by the y point of the second point, and then you do a minus the y of the first point multiplied by the x of the second point, and then you just increase the indices by that. And when you get to the last one, 6, it needs to loop around with the P1 again. So doing this calculation in absolute value and divided by 2 will give you the area of a polygon. And if you want to play around with this, web page is really good. It explains the formula, and it also allows you to play with some points there. And these points are going to be draggable. And every time you drag it, you get a new value for the area there. So you can leave here if you're, you can read here if you're not familiar with this formula. But it's just a formula. Okay. Now this formula works even if your polygon is concave. If you don't know what the concave polygon is, it's the one that has a possibility to hold water on some of the sides, like for example here. So this is a convex polygon, it's called convex. This is a concave polygon, and both of these, the formula works for them, but the formula does not work if your polygon has intersections in it, self-intersections in it. So for this case, it will give some kind of strange result. But what we are going to draw here in this interface is most likely going to look something like that, not something like that. So I'm going to use this area of a polygon and invent a measure for the roundness. Now this roundness, to calculate how round a polygon is, if we look here, there are plenty of papers on how to do this and many approaches to do this. Even we have one for GPS trajectories. So how round are GPS trajectories? We have some kind of method for measuring that quickly. But I'm going to try to explain a quite intuitive alternative approach. So having this polygon, I assume you can figure out how we can get its perimeter, this length. You just add up all these sides. It's quite easy to calculate this perimeter. And the area, we saw already a formula here for how to get it. It's almost the same as adding the values, but some multiplication there. So if you do this formula, and if you add the lengths, then you have the area and you have also the perimeter. Now, these two objects here have the same length, the same distance here, but this one has a larger area on the right. Actually, it can be proven that the circle is going to have a maximum area compared to if you take the sides of the circle and you move them a little bit inside or make it a little square side, whatever. You can also visualize this polygon from here and blowing it up like a balloon. If you are going to inflate this polygon, at some point the area just gets bigger and bigger until it becomes this circle. Think about these. Think about those as rope, actually, not as a balloon, because the balloon is stretchy. But this kind of rope stuff. So anytime I have this kind of irregular polygon here, I can increase its area by somehow blowing it up. So it becomes like this. So more or less, if I know the perimeter of an object, I could calculate what is the area of the circle that it could have potentially if it would be inflated. And you can look at this. So the perimeter of the circle is 2 pi r. Okay, so 2 pi r is the length of the circle knowing r, but I can inversely get r. So here we know the perimeter, it's just adding up all of these things. So I could just get r by dividing p to 2 pi. And then the maximum area of this polygon is going to be pi multiplied by this r squared. So the maximum area of this polygon is going to be the area of the circle if this perimeter would be inflated as maximum as possible. And if my initial polygon is going to be a very, very round polygon, area is going to be equal to max area. If my initial input is a circle, then it can't be inflated anymore. So area here would be equal to max area, but a roundness measure could be calculated as area divided by this max area. So anytime, for example, in this case, this looks maybe like half the area of the circle. Like it's quite squished. It's almost like this is zero area here. And I'm inflating it. So this would be maximum area. So I could measure the roundness as whatever this area is, and I have formula for that, and divide it by the maximum possible area that whatever I'm drawing, whatever my polygon could potentially have. And that's going to be more or less the decision for having you pass the level or stay on the level, or whatever in our game. So it's interesting, but I think we may have even time for doing this now. Any questions? Maybe we take it simpler because many things happened today, and yeah. Maybe I ask for questions first. From Joensuu and from Kuopio. Who is very confused? Okay, nobody is confused. Yeah. Yes?
Almost everyone.
Sorry?
Almost everyone is confused.
Almost everyone is confused. Okay. Yeah, many things happened today, and somehow. So, how about you ask me questions for the rest of the lesson today? Like, if you don't understand something, or if you don't understand where I'm heading, or somehow my lesson today wasn't as good as I planned.
It was good.
I'm sorry?
It was good. I understood it.
You understood it?
Yeah.
Oh, okay. So everybody is on the same page with me. Okay, I'm really shocked. Okay. Okay, I will leave this area computation for tomorrow, but today we will talk more about projects, and I will show you a couple of videos that I recorded in the weekend. And I will also show you how to load the video in your app instead of the camera initialization. So here I have initialize camera function. I'm going to go right next to it, and I'm going to paste another function. It's very similar to the other one, but I don't want to waste time writing it. So what it does is it initializes the video on the canvas. It starts again this process video frame function, same interval. The only difference is it doesn't come from the camera, so the signal doesn't come from the camera. It actually comes from a file on the server. And then I tell it to load. I also tell it to be muted. And this is maybe a little bit strange to you. If I don't make it mute, it won't work. Because browsers tend to have a problem with starting sound without a permission. Like, you don't want to have tabs that are opening and all of a sudden some noise comes from one tab. So to make the voice come, it's a little bit more work to do, but we won't need it, and this way it's going to start playing without a problem. So instead of calling initialize camera here, I'm going to call initialize video, and it's a hard-coded link what I have in that video there. But if I refresh the page now, it shows me and drawing something with this same marker thing on top, but in a much smaller screen. So the reason why I made this video is first of all because of this lag. So there is a huge lag here, and if I were to go and open this from the other computer, at least here in Kuopio, it should look much better than in the other place. So this lag effect that the cursor was constantly jumping more or less, it's gone. It's able to process it faster, and that's the same way I see it on my laptop, but because of this Bridget connection, it's a little bit of a problem. And in Joensuu, if you want to see this video, you can also enter this link. So if one of you opens this page there, then you could see it going faster. And in the same directory, I have a second video. And this one could be used by you for the third project. So in this second video, I'm going to start it. I'm doing something else. I'm more or less trying to draw something, again with this kind of marker thing there, but I'm also attempting to change color. So this is more or less your task. Can you make it so that when the green pointer is detected on different parts of the screen, instead of drawing there, you have like a color palette, like this, what the painter is using in his hand. So more or less I'm trying to do a drawing here, but if I'm moving towards these kind of corners of the screen, I want that command to do something else instead. So you can work with this video, and in this version of the program that we wrote today, it does draw something, but now it also cuts the beginning part of the okay, I didn't think about that. The beginning part of the drawing. Yeah. So your job is going to be more or less, if you don't have a webcam, or if you prefer to use this instead of your own person there, or if you don't want to worry about lighting conditions when you present at presentation or whatever. So this is more or less like a less noisy input that you can build your application on. Now we can talk about this. But the main idea is I'm drawing something here, and I would like the color or something to change when I'm doing something else than drawing like now. So this gesture should indicate that change color. You could, for example, mark the screen like this.
You can't see.
Oh, I'm sorry. So I was referring that you could, for example, mark the screen something like this. And then whenever my hand moves in one of those areas, you have to detect that, hey, this location is inside this area here, or of course it could be square or whatever you want it to be. And then when it is there, it changes the property of the line that is being drawn here. So at least that would be like a requirement for this project that also uses the camera. So of course your project is going to work if you switch it to the webcam mode, and then you stay there, and then when you ever want to change the color, you're gonna do something like this. But the video is more or less for those who don't have a webcam, or for those who don't want to debug like this all day. Like debugging like this can be quite tedious and time-consuming. Okay, now questions about this project. Before I write the specs, I thought I'd present it now. Is this difficult? Okay, some guys say no. How about here?
ask a question?
Yes?
So you said we're gonna have like five projects, right?
Yes.
So you wrote something like you can do like 4 out of 5.
Yes.
So if you do 4 out of 5, you're good.
Yes.
Okay.
But you were topping it, right?
Yeah.
Yeah. But more or less, the last project is quite related to this project. I mean, similar. Again, this kind of the image handling.
Yeah, I'm just asking just general.
Yeah. Okay. So if this is clear, then that's great. So tomorrow we're going to finish this this effect. We will start with this kind of measuring the roundness. We already talked today about the formulas a little bit, but tomorrow we implement them, and then we're going to put a few particles as an effect over the video. And that's more or less it. If you want it to look much better, then you can do more by yourselves. Okay. But yeah, so we'll see you tomorrow.